Welcome back to ECE 501B. This is our last time together as a class for you learning or us learning together. The next time we meet, you're going to demonstrate your knowledge, which is the final exam in here at 3:30 on Monday. So that's less than a week away that you need to make sure you're here, and it's going to be 30 minutes before you normally come to class. But it's a 2-hour exam, and I will talk a little bit about that at the beginning of this class. But now, just as a heads up, I'm providing 6 hours of office hours between now and then that might be useful. Maybe you on Monday, I hope those are very trivial last-minute questions, but if you have something over the weekend, you could email me, and if we can't seem to get it, sometimes it's not the easiest to try to do via email, but maybe you can get the process started via email, and we can come in, and in 10 minutes we can figure out your particular concept that you're struggling with or some particular point if you need to, but the final will be an hour and a half after office hours close on Monday. Question? Oh, my office, I didn't indicate, did I? It's ECE 523. So it's on the fifth. Well, I have several offices, but this is the one. This is the one where you will find me for office hours. For these 6 hours. That's the plan. I'm kind of booked in a lot of, so these are not consistent with the normal Thursday and Friday office hours that I've had all semester. These are now different because my mornings have been overbooked when class is no longer in session. But there's 6 hours there that we can talk about the issues dealing with 501B and what you'll be needing to know for the final exam. And one thing that you have to do before that, you have to do before midnight tonight, is the TCE, the Teacher Course Evaluation. That's due today. And I would appreciate your input, your feedback. My other class this morning, I said, well, this is a controls class, and we are talking about feedback, and I can now use your feedback to change or adjust the behavior the next time I teach the class, and that's what we can say will happen for your feedback in this class also. Questions on what you're responsible for? The other thing that I guess is due, which I forgot to put, is your project. That's due tonight, right? So make sure you get that turned in also. Here's the process for the final. 4 sheets of notes. It is comprehensive. I didn't say that, but it is covering from the first chapter of our first textbook, theoretically through the end of the second textbook, but we will be lucky if we get through 2 chapters of the second textbook today. And that material won't be emphasized on the final exam. We've spent 2 lectures, 1 lecture so far on that material. We're going to spend this second lecture on that material, but I hope that you at least start to hear some ideas or concepts in today, and you can start to go back and dig in deeper if you need to, if you're dealing with functional analysis and the areas or the application areas where that might be applied. But I think this particular process for the final is consistent with what we've done so far this semester. Are there questions about the final? That's at 3:30 on Monday, and it's 2 hours. And it will be, did I say 8 questions maybe? And I think we've had 4 or 5 during the normal 75 minutes, so it's about the same kind of processing. There may be some show, some proofs, maybe some find, like find eigenvalues and eigenvectors, show this is. or has or proved this. So it's the same kind of style as the others, and there is a practice, or there, not a practice, but there is a discussion of the final on D2L in another unit called Final Exam Material. What we want to talk about today is this idea of infinite dimensional spaces, and actually what I'm going to do is I'm going to sort of just talk about this outline that really sort of gets us through the first two chapters of the second textbook, which is Frank's signal theory. And then we'll start looking at it from the top and working our way back down. But I want to at least sort of tell you how it's laid out, or what you might see in the first two chapters of the book. And here we start with signal sets, just like we started with sort of vectors in the finite dimensional setting. Now we are starting with signals. We then want to somehow partition or group certain signals. So now we're going to have sets of sets. We want to figure out, can we now classify these signals in certain sets? And once we have that, then we will, and that partitioning can be done with equivalence. And this, I think, we'll get there today. This will start to become clear. And we can make these equivalence sets very trivial, meaning we might say at a given point in time, T naught, is this signal positive or is it negative? We're going to not worry about it if it's 0. We'll say at, let's say, 2.3 seconds, is this function positive or is it negative? If it's positive, it goes in this set. If it's negative, it goes in this set. Now we've classified all of these signals, let's say, that are bouncing around between time t equals 0 and time t equal 2. And we really don't care how they're bouncing around so much as what's happening right at t naught equal to 2.3. But do you see now, if I gave you 100 functions or an infinite number of functions, you could now classify those. You could throw them in two different buckets. A positive bucket, a set, and another negative set bucket, just based on that as a way of making these functions equivalent to each other. All the waveforms, and one might be spending most of its time negative, and then it pops up and it's positive. Well, that will get thrown into the positive bucket, and it's now equivalent to some of these others, and maybe one of those was always positive for all time between A and B, or 0 and 4. And those are now equivalent functions. They go into this set that's a positive set. Once we have these functions or signals in sets, it might be nice now to compare those signals. And how do we compare? How far apart are they? Or how do they, maybe one, how many times do they go through 0? Or how far apart are they? How do we measure this? We might need to put some kind of distance, or what's called a metric. We can define a metric between two elements in a set, and now think two functions in a set. Once we've collected or combined a distance with these sets, now we have a metric space. We have a space that we can now sort of think of geometrically. You give me two signals in a set, and I can tell you the distance between those signals by some metric. And you might define a distance or a metric. You might define a metric. We might have 30 different metrics, and that means we have 30 different metric spaces. And they may all have certain characteristics that you like in terms of, that's why you defined your metric the way you did. But there are, let's say, conditions for something to be a metric, and we'll talk about that. What qualifies as a metric? But once you have this metric, now you can create many different metric spaces. Once we have distance, now we can sort of talk about, oh, if we had a sequence of functions, they may be converging or not based on this distance. Are they getting closer together in this sequence of functions? That's this idea of convergence. And we also might want to talk about continuity of maps. Maybe we have a set of functions and we want to map that into another set that might just be the real numbers. That might be called a functional, and we would like to know, is that map continuous? And that will tell us a fair amount. But once we can talk about convergence and continuity once we have this concept of distance. Again, we're trying to make some geometric notion for these squiggly functions that we might be dealing with. Has anyone heard of Cauchy, a Cauchy sequence? Some of you might have. If we have a sequence of elements in this set that are converging, then that means we actually have a Cauchy sequence. As we're getting closer to a, let's say, the limiting point where these elements are approaching, then each subsequent element, those are getting closer to each other. If we looked at a pair, far enough or close enough to that point, and that's what we mean by Cauchy. We're really saying as this sequence evolves or marches through indexes, now if M and N in that sequence are close or they're getting closer, that's a Cauchy sequence. A lot of terminology, and I'm just wanting you to sort of take it all in, see the big picture from this. And I have lines going crazy on this screen or of this outline of the first two chapters of Frank's. We have a metric space because we have signal sets and we have a metric. We have a metric space. We can call that metric space complete if every Cauchy sequence actually has a limit or converges, or that that sequence of elements is actually approaching a element in our set. And we'll talk a little bit about where we could actually have these functions or elements approaching a final value or a limit, but that limit may not be in our set. And then that would mean that our set is not complete. It's missing some points that we want to act, or some elements that we want to approach, or that our Cauchy sequence is trying to approach. So when we talk about convergent, that means that the limit of this sequence of functions or elements actually belongs to our set. And you could even think as easily as the real number line between, let's say it was open at 0 and closed at 1, maybe a segment of the real number line. You could create a sequence of points that is marching towards the origin. Maybe it's converging to 0, but since 0 is not in that set, it's open at 0, it wouldn't be a Cauchy sequence. That's kind of the idea. And this may be kind of hard to capture just by me talking about it, but you can start to draw pictures and see if this makes sense. One thing that you want to keep in mind when people start talking about a sequence converging or a Cauchy sequence, if something is converging, you can actually, that implies that you could find a Cauchy sequence in that set. But if you have a Cauchy sequence, that doesn't necessarily imply that it's going to be a convergent sequence of elements. And that's because the limit, like the origin, may not belong to the set itself. And we'll look at a particular function, if we have time, relative to that notion. Then we get into different kinds of how can we sort of characterize these metric spaces. And you might hear something saying it's a separable metric space or it's a compact metric space, and think now of sort of covering this, maybe just the interval of the real line with open sets or open balls or open disks. And if you can now cover that interval on the real line with a countable number of open sets, then that would be a separable metric space. If you can actually cover it with a finite number of open sets, then it is a compact metric space. Those we won't get too much into because it's not needed for what we're wanting to do, but having a separable or a compact metric space actually allows us to say maybe a little bit more when we're dealing with mappings between one set and another. And when we're talking about mappings, remember the V's and the W's, or the U's and the V's. When we were in our finite dimensional, we always had a domain. Where were we starting and where were we finishing? You can have the same thing in these infinite dimensional settings with some kind of map, where you now might be mapping from these functions into the real line, for example. Once we have these metric spaces, then we can start adding on to or incorporating or allowing them to have a couple of operations, an operation of addition and multiplication, just like we've done with vectors. How do we define vector addition, and how do we define scalar multiplication? We can do the same thing here with these signal spaces to get linear spaces, and then we can actually combine those elements. Now that we can do addition and scalar multiplication, just think of what we did with vectors. We had alpha 1 x1 plus alpha 2 x2 plus alpha 5 x5, and now we had a 5-dimensional space. Now you can have a bunch of alphas with f's, for example, and you can just continue to add linearly independent directions, so to speak, or functions by these linear combinations, and we can take a collection of those or a subset of those to get linear subspaces, consistent with what we've done in finite dimensions. Now, we talked about a metric. We can also talk about a norm, and we can define what we mean by a norm, but now we can impose a norm on that linear space, and this gives us a way of classifying the lengths of these elements in these sets. And now we get to sort of some new terminology, a Banach space. Now we have this collection of terms that when placed together, now we have a normed linear space that is complete. That means that our limits are going to live in the space itself. And we have a norm on that space. We can identify distances, and that's a Banach space. A norm is not quite an inner product. An inner product is sort of the next step up in terms of what it allows us to do. An inner product, remember, allowed us to sort of talk about angles. The norm was distances or lengths. The inner product now allowed us to talk about angles, and in particular, when things are orthogonal. If we can now define an inner product, which now just think of an integral of a function f1 of t times f sub 2's complex conjugate of t between two limits, that could be an inner product on these function spaces. And if they are orthogonal, that means that the inner product is giving us a 0 result. And that's the main angle that we're interested in. We might like to keep all of these functions orthogonal to each other so that we now go in a new direction as we add more and more. And that's sort of what you're doing with Fourier series. You're adding up, and each time you add, you're sort of going in a new direction with these sines and cosines. Once we have an inner product, again, which is a little bit stronger than a normed linear space, now if we have an inner product space that is complete, meaning all of these sequences, wherever they're going, they stay in the space that we start in, then it's complete. Then we have a Hilbert space. So we have a little bit more specific concept or entity if we have a Hilbert space versus a Banach space. So you can sort of see this inclusion. All Hilbert spaces are Banach spaces, and all Banach spaces are normed signal spaces, and that's in this signal space. So you could sort of think of these collapsing sets or expanding sets depending on which direction you're going. But the Hilbert space is more specialized than Banach, which is more specialized than normed, which is more specialized than just signal space. Once we have this inner product, we can start talking about how do we locate signals in time. And that's what the textbook calls this time ambiguity function. Meaning it'd be nice if, let's say, this was some communication signal, that we knew exactly when that communication took place. The time was not ambiguity, or there was no ambiguity in when we know when that signal arrived or was present. And it would be nice then if there is a lot of distinction in our time, very little ambiguity in when that signal was present or not, that we would have some number maybe that's large, and we could say, oh, the inner product is huge relative to this signal, so let's now use that signal as a way of communicating, because now it's very clear when that signal is present or not because of this time ambiguity behavior. It's very clear when it's on and when it's off. So that you may want this signal to be having a large inner product between when it is aligned with itself and when it's maybe offset in time with itself. And you might be hearing things related to correlation, autocorrelation. When is it aligned with itself versus when is it offset in time, and hopefully it's very small, the inner product, when it's offset in time. So that difference might be related to these inner products, and we now have this huge number associated with a particular signal or function, and we can use that now maybe in a communication sense as a time ambiguity. We have very little ambiguity in when that signal happened in time. And all of this is available to us because we can now think of correlation or inner products with signals, with pairs of signals. So we can look at a signal correlated with itself or inner product with itself, or a signal and a time shift of that signal. And now we can start looking at when is this, or what kind of a signal could we build that would not be, or that would be very easy to determine when it was present or when it was not present. There was very little ambiguity in when it happened. That's what they're sort of meaning by this time ambiguity function. Once we have these inner products, these directions or angles, we can start building up functions that serve as bases. And we can talk about basis signals that are orthogonal now that we have an inner product. And once we have a metric or a distance, we can normalize those signals so that we can not only make them orthogonal, but we can make each one of them, we can normalize it. And those are nice to have, as we've learned in our analysis in finite dimensional discussions. And it allows us to think about continually either removing or building up in orthogonal directions these linearly independent vectors, so that we know that if we add just a little bit more, we're going in an orthogonal direction to everything that we've done before, so that's the best direction to move in, or is a good direction to move in to add more information in whatever process that we're playing with. And that's now that Graham-Schmidt process is available to us in this signal space or in this function space environment. That's basically the first two chapters. Let's now step back and go through that in a little bit more detail. And I don't know how far we will get, but at least you'll start to see maybe an explanation of what you can read in chapters 1 and 2. And the very first place that we want to start is with these sets of signals. How do we start to label or classify signals into different sets? And again, keep thinking back how we started in the first chapter of the finite dimensional. Now we said we have these vectors, and we'll start building up properties associated with these vectors, or these signals now in this case. Here, now let's recall that in the finite dimensional case, we started with a set of vectors. Similar to that, though, but now in a different way. Now we're going to start with a set of signals, not vectors. Now these are going to be signals. Here we will start with a set of signals. Let's look at some examples of sets of signals. For example, sinusoids. We could now build up a set of sinusoids. Let me call that capital S sub S as the set of X. X here can be a signal, so this might be a parameterized function. X might be of t, such that x of t is equal to the real part of e to the alpha plus j 2 pi f t plus theta, where t is allowed maybe to be infinite in duration from minus infinity to infinity, and alpha that's in the exponent, maybe this f, which is frequency, and maybe theta, which is phase. Maybe we allow all three of those to be real, coming to us from the real numbers. E to the alpha, that's just some number. That's now the, so we could now that we're playing with an exponent, we could separate that into a product, e to the alpha and e to the j. The e to the alpha is just an amplitude, whatever alpha is. So that's the amplitude of our sinusoid, a cosine or a sine. And the e to the j, we know that's this rotating phasor. And if we just look at the real part of it, now we can view that as a sine or a cosine with a certain amplitude given to us by e to the alpha, which means you give me an alpha, f, and a theta, and a t, I can parameterize all of these sinusoids. That's now the set of sinusoids. Or we could call or create another set of sinusoids by doing it a little bit differently. Now we might say, let's look at the set of functions x such that the second partial of x with respect to time plus lambda squared x is equal to 0. Now we're asking or saying this set of functions x are such that the second partial of x with respect to time plus a positive number, lambda squared, times that original x must equal 0. This also is a sine or cosine waveform, where we still are allowing time to be from minus infinity to infinity, and now lambda, let's say, is some real number. That's also another way of representing or collecting sinusoids as a set. What are some other sets? So there's one set. Another set might be to have a set of functions that are energy limited. Let's say energy limited signals, where we might call these, let's say, S sub e of k, where that capital K is actually the limit on the energy. And sub e just means these are energy signals, or signals x, such that we integrate from minus infinity to infinity of the square of that signal dt, and as long as that's less than or equal to k, which is, let's say, less than infinity, where k is now real, and let's say that it's bigger than 0, that could now represent a set or a collection of signals that are energy limited, x's that satisfy that particular definition. We're just trying to talk about different sets, and then we might start doing something with these. What if we looked at duration limited signals? By that, now we're saying, let's say that that's S, capital S sub d of t. That's now signals x such that x of t is equal to 0 for all time, let's say, bigger than cap t. That's really just saying that we want to look at all signals x that are 0 after a certain big value of time, or it could be a small value of time, whatever capital T is. This is now 0 outside of these limits given by capital T. And if somebody said, oh, I have a signal x that belongs to S sub d of t1, what does that imply about x and S sub d of t sub 2 if t sub 2, let's say, is bigger than or equal to t sub 1. Is this an element of or not an element of s sub d of t sub 2? So that's what I'm asking now. Fill in the blank. What is it relative to this definition of duration-limited signals? And if it's not clear what I'm trying to ask, I'm now saying I now have, let's say here are my x of t's, just a representative, and I now have t1 and t2. Here's minus t1 and minus t2. If x belongs to s sub d of t1, then I know that my x of t looks like that. It's 0 outside of capital T1. So what does that mean relative to x and this set of other signals where t sub 2 is bigger than T1? It belongs to that also, doesn't it? So now we've convinced ourselves just by this simple picture that if I gave you two sets, s sub d of t sub 1 and s sub d of t sub 2, if I told you how t sub 1 and t sub 2 were related, and if I said one signal is in one of the sets, you could tell me something about the other, or the possibility. If I now told you that I had a signal x in s sub d of t sub 2, could you tell me definitively anything about x and s sub d of t sub 1? If T1 and T2 are related as indicated here. Could you definitively tell me something about whether x belongs or does not in s sub d of t sub 1? No, you couldn't tell me without more information, could you? Is that clear? So now you can see how these sets could be bigger or smaller in terms of the number of signals that belong to those. Here is a duration-limited signal. We can do the same thing. Since this is electrical and computer engineering, we like to sort of bounce between time domain and frequency domain. We could also talk about band-limited signals. There, let's say that we now are saying we have S sub b of w. That means that we have a set of signals x such that x of f, and maybe I should have, well, maybe what I can do, let me do the following. Let me make that a little bit more distinctive. Let me call this capital X of s is now equal to this integral from minus infinity to infinity of x of t e to the minus j 2 pi ft dt. And now we want that actually to be equal to 0 for all f greater than w. Meaning we want capital X of f, or if you were sort of thinking about this, we want no signal energy outside of or beyond this frequency of omega relative to the frequency axis f. Omega is just some mark. And again, we could look at this as f, and here is maybe our x of f. This might be minus omega, and here's plus omega. Now we're saying something maybe like that. Now this is a function of frequency, where we're saying that beyond a frequency of omega, we now are forcing that signal, little x of t, to have zero energy outside that frequency of omega. And that would then be called a band-limited signal. These are now different sets of signals, but once we've created these or identified different sets, now we can play with sets, just like we've played with sets throughout. We can now apply set operations like union and intersection to signal sets. As an example, suppose I wanted to know, I now want to take the intersection of a time duration set of signals, S sub d of capital T, intersect that with the set of band-limited signals. What's that set look like? We now have signals that are duration limited. Think pulse. Now we have pulses that are only so wide, and we want to intersect those with a set that has restrictions on the frequency content. It doesn't have high frequency content as a part of it. What's the intersection of those two sets? And now you sort of have to go back to your Fourier transform ideas from your undergraduate days and say, what does the, let's say, frequency content of a pulse look like? What's its Fourier transform? What's its frequency content? Do you remember what a pulse might look like in terms of its Fourier transform? Do you remember, well, now I'm wanting to go wash dishes, so I need to go to the sink. Do you remember the sink function and what it might look like? So now if you took the Fourier transform of a pulse, that might give you a sync waveform in the frequency domain. And this sync waveform just keeps going on and on. It has all the frequencies in it, and it needs all those frequencies to build up these sharp edges on this pulse. Now, the energy in that sync may be concentrated in a certain frequency interval, but it theoretically is infinitely in extent in terms of how many frequencies it possesses. So in fact, if you have a finite duration time domain waveform, it has to have all frequencies present, meaning the intersection of a band-limited set of frequencies and a finite time duration set of signals is not the empty set, it's the zero signal. It's the signal x such that x of t is equal to 0 for all t. So this is something that will allow you or make you just want to go back and start looking at your Fourier transform material. The only signal that is both band limited, only contains a finite bandwidth, it's band limited, and duration limited, is the zero signal. And let me just give us a note so that when you're going back through your notes in 10 years or something and just enjoying this experience again, you can say, oh, that's what he was talking about. I need to pull out my Fourier transform material. Recall the Fourier transform of a finite duration pulse waveform. By that I'm just meaning maybe we have something like that in terms of x of t. That's a finite dimensional pulse waveform, and its Fourier transform is a sinc. A non-trivial signal, so that means something other than the zero signal. A non-trivial signal cannot be both time duration limited and bandwidth limited. So now we have these sets. We've now covered the first bullet in our 20 bullets that we started the class with. We need to get through the other 19. May not make it. But now that we have these sets of signals, can we partition these signals into pieces or separate them in some way? Let's now talk about sets of sets, or this notion of a set partition. The set of sets, we could now have set 1, set 2, let's say set sub n. Now we could say that that forms a partition of some larger set S. Form a partition of this, let's say, fundamental set S, which is S1 union, S2 union, S3 union up to S sub n. It forms a partition only under certain conditions, meaning S is a union of all of these sets if we looked at set I, sub I, and intersected that with set J for all I and J, and they gave us 0. So there's no intersection for all I and J that aren't equal to each other. Then this set of sets forms a partition of the large set. So this is like the direct sum decomposition in our finite dimensional setting. Now we have this set that I'm drawing as some oval, and we might now partition that into non-overlapping sets, let's say S sub 1, S sub 2, S sub 3, S sub 4, and S sub 5. And having this partition of a set allows us to neatly break this or separate this larger set into pieces or parts. A partition neatly divides a set. Now, it may not be easy to try to create these divisions or these partitions or these sets that break up a large set. And for that reason, sometimes it's easier to develop a relation that defines elements of this larger set as being equivalent, and if they're equivalent, we'll group those into one of these subsets, S sub 1, S sub 2, etc. So often it's easiest, or the easiest way to get or obtain a partition is via an equivalence relation. Where now two elements, this could be two signals, two elements are equivalent if X wiggle Y. I'm getting very mathematical and using this wiggle notation. So X wiggle Y means that X is equivalent to Y. So two elements are equivalent if A, they meet the following three relations. X wiggle X. X is equivalent to itself for all X in this set. That's A. B, if X is equivalent to Y, then that actually implies that Y is equivalent to X for all X and Y. And the third property for two elements to be equivalent would be if X is equivalent to Y and Y is equivalent to Z, then that implies that X is equivalent to Z for all elements X, Y, and Z. So it may be easier to define a relation, an equivalence relation, that allows us now to basically compartmentalize or put into sort of subsets of this larger set, or partition this big set by using these an equivalence relation. And there are all sorts of ways that you can define signals to be equivalent. Note, there are an infinite number of possible definitions of what makes two things or two elements equivalent. We just need our rule. Rule just has to obey those three relationships. And if we have those relationships, X is equivalent, or X is wiggle X, X wiggle Y implies Y wiggle X, and X wiggle Y and Y wiggle Z implies X wiggle Z. Application of an equivalence rule creates equivalence sets or equivalence classes. Meaning we could create a set S sub x that consists of all elements y such that y is equivalent to some signal that we've picked, x, by a particular equivalence. And once we have these equivalence sets, that allows us to form a partition of our underlying set. And we can go either direction. We could find equivalence sets to break this up into different partitions, or we could have somebody has already identified some partition, or any partition can define an equivalence set or an equivalence rule. Let's look at an example. For example, consider the underlying set being the set of integers. Consider the set of integers. Let's now say that that's our capital S. Capital S now are n, any n, such that n is equal to 0, plus and minus 1, plus and minus 2. Any integer, positive or negative, belongs to capital S. Now it might be nice to partition that set. And one sort of obvious way might be, let's just do it evens and odds. Odd integers will be one set, even integers will be another. Now we've got two sets that partition this set of integers. So that now we could say modulo 2 congruence allows us to generate two equivalence sets. Where now we could have S sub 1 being the set of n such that n is equal to plus and minus 1, plus and minus 3, plus and minus 5, etc. There is our odd, not strange or weird, just odd in terms of numbers. And S sub 2, the other partition of our set of integers n, is now n equals 0, plus and minus 2, plus and minus 4, etc. That's one way of, or an example of partitioning a set. So the set that we began with was the set of integers. We can now break that into two equivalence sets. You give me an n, and it'll belong in either S1 or S2. It's not going to be in both. What's another example? Suppose we now, and this I was talking about earlier, consider the set of all signals except, or all the signals that I want to talk about are the signals except for the set that's equal to 0 at time t0. Consider the set of all signals except for, and now I'm using the zero signal in a particular way. My zero signal S sub 0 is the set of x such that x at some time t naught is equal to 0. This is now the signals they may be non-zero in all places, but right at t naught they equal 0. We want all the signals that are not identically 0 or equal to 0 at t naught. Let's consider all of those signals. Now if we have that, we can, like we did before, we can create two different sets, or we can partition our big set that doesn't contain S sub 0. We can define a partition, let's say S plus, to be the set of x such that x of t naught is positive, and S sub minus are the signals x such that x at time t naught is negative. And this now allows us to partition or create an equivalence rule. So this partition of our signals, of our set, allows us to now generate an equivalence rule. This partition can be used to define an equivalence rule, where our equivalence rule could say something like the following. That could say x wiggle y, x is equivalent to y if x at time t0, y at time t0 is greater than 0. And then all signals would go into one or two of those, one or the other of those S plus or S minus signal sets. Meaning, if we simply drew a picture again of something like this, partitioning with S plus and S minus, we could draw something that maybe looks like the following. Maybe we have a signal F1, and maybe we have a signal F sub 3, and maybe we have a signal F sub 2, and maybe we have another signal F sub 4. And maybe we are interested in these signals between, let's say, some time t between little a and little b. And our partition now is concerned with what's happening to those signals at some instant of time. These are now our signals f, or I guess maybe I should have had, these are now x's, aren't they? If I'm using the same notation, this would be x1, x2, x3. But now you can classify these four functions into either s sub plus or s sub minus based on this definition of t naught. For example, what is or which set does f sub 1 belong to? F sub plus or F sub minus? So that's now S plus. We're just looking at, and these waveforms or functions may be completely different relative to every point other than T naught, but right at T naught is what we're using to classify or partition these waveforms. F sub 1 is S sub plus. F sub 2, what does that belong to? Plus. F sub 3, that one's minus. F sub 4, that one maybe is easier to see, right? That one's always negative, which means that we could say that F1 wiggle F2. Since F sub 1 at T naught times F sub 2 of T naught is positive. And we could also say that F sub 1 is not equivalent to F sub 3, since F sub 1 of T naught and F sub 3 of T naught, now we have a positive times a negative, that's negative. We can now then say that note that equivalence sets or equivalence classes can be represented by a particular member of that set, can be represented by a characteristic member, call that x hat. Meaning we could define some set S sub x hat are the set, or it's the set of signals x such that x is equivalent to x hat. And it really does not matter which characteristic member we pick. So now we've looked at a way to sort of partition and collect different signals into sets. Now it would be nice to compare signals within a set. We've just now classified them. Now it might be nice to say, how are x1 and x2 related? How many times do they cross the zero axis? Or how close are they in some sense? And now we want to talk about some geometric notions or ideas, and that's giving us now the signal spaces question. So now we are saying that our underlying, so the question I think was, how did I define my underlying set? And it's now this. It's this big set that if you have a signal that's 0 at T naught, that's not in the big set. Just throw it out. So now if I'm looking at this collection of functions between A and B, if any of those functions are 0 at time T naught, let's just discard them and only play with the sets that are left. You could arbitrarily say, well, let's just put all of those that are 0 at t naught into the positive bin if we wanted to. But here we just said, let's not even worry about what's happening at t naught. Let's just throw those signals away. And once those are gone, now let's just classify them as S plus or S minus. Is that? Oh, the earlier example? This one? Okay. What was your question again? So now the intersection of S1 and S2 does not include the 0 element. Oh, so now maybe it's a function of, did I, right here, maybe I should say that that's the empty set. Maybe I should say something like, we really do not want anything to be shared between them. It kind of depends on what you're playing with, but in your case, I would say we want those sets to be empty, the intersection. So maybe that's a better way to label that or to show that. So now we want, if we're partitioning the underlying set, we want really no overlap, nothing shared in these signals or between these signals in the different partitions or equivalent sets. Does that answer your question? So now we don't want any overlap in these sets or these partitions. But in order to get these signal spaces, what we want to do is create a distance. And a distance, so now what we want is we want to say, okay, these signal sets and a distance will produce a signal space. And the distance that we can look at involves two different elements or two different functions in a set, where a distance function, and now I'm sort of really quickly going through this, but a distance definition, D, is referred to as a metric if this distance definition satisfies the following three properties. A, this distance between two elements, x and y, so think of x as a signal and y as a signal, is greater than or equal to 0. And the only way that we can have the distance between x and y equaling 0 is if x is equal to y. If the distance between x and y, we calculate it, and then we basically exchange the elements in the slots, we better get the same distance. The distance from x to y is the same as the distance from y to x. And finally, we have this notion that's like the triangle inequality, which says that the distance between x and z is less than or equal to the distance of xy plus the distance of yz. And if you looked at this in terms of functions, you might say something like the following. You might say one distance measure between x and y you could define maybe as an integral between a and b of the absolute value of x of t minus y of t dt. That might be one metric, and you could look to see if it satisfies those three conditions. A second metric, d sub 2 of xy. That now, and so there, that's the integral of the norm of x minus y to the 1. Then take the first root of that. Now let's look at the integral from x to y of x of t minus y of t squared dt, and now take the square root of that. And that's our Euclidean distance or metric in these signal spaces. And let's say d sub 3 of xy is now the sup, now we're getting hungry, but the supremum of the absolute value of x of t and y of t, or where the sup is just meaning the least upper bound. So the sup is this least upper bound. But these are now like the 1 norm, the 2 norm, the 3 norm, and if you combined these sets with these different metrics, you get different metric spaces. And unfortunately, all we got to were the norms on these spaces. You'll have to read on to learn about inner products and what you can do with continuity, etc., with these elements in function spaces. But we talked a little bit about that in the overview in the lead-in to this class.